I will now formally prove that the determinant is linear as a mapping in its jth row. So t of x plus y is defined as a determinant of the matrix with rows vi, and on the jth row we find back x plus the vector y. These are row vectors. So writing down the definition of a determinant, this is no more than summing over all patterns p, and then take the sign of p times the product of p defined on this matrix. So this is no more than the sign of p, and now we're going to write more explicitly what is it actually in the product. So if I take I unequal to j, then I'm summing over the ith vector, row vector, and I choose element pi, times what I pick from the jth column, or jth row, is actually pj, so x plus y pj. So rewriting this gives us actually the same terms, vi pi times the sum of the jth element from the row vector x and the jth element from the row vector y. So the strategy should be clear. We're now going to split this sum in two parts, one dealing with x and one dealing with y. And so this equals the sum of all patterns of the sign of this pattern p times the product of I unequal to j vi pj x pj, plus a similar part where the only thing that changes is that we write y instead of x pj. And now it's easily seen that actually the first part in the sum is t of x and the second part is t of y. So in order to have a linear mapping, we also need to have that the mapping of k times x equals k times t of x. So we now write the determinant again, and instead of x we write k times x, so this is a scalar. So writing is down through the definition of the determinant, we again get the product of I unequal to j of vi pi times, well, what do we get? X pi times k, of x pj times k. So now we're going to take out k from these products and put it outside the sum. So we get the sum of the sign of p times the product of I unequal to j vi pi times x pj, which is actually k times the determinant of the matrix with the jth row equal to 2x. So this is k times t of x.